Hi, my name is Saket Kenjale, and in today's video we're going to be covering section 1.3 trigonometric functions. And so we're first going to start with radian measure. So first, what is radian? A radian is a unit for measuring angles, and it's more natural than degrees because they are directly related to the unit circle. And right here, this diagram shows the conversion from degrees to radians, and it goes from 0 degrees all the way to 180 degrees, or 0 radians all the way to pi radians. So now let's look at an example problem, example 1.22. So part A says express 225 degrees using radians. And the way you'd want to approach converting from degrees to radians is that you want to multiply whatever degree value you have by pi over 180. So when you do that, it will become equal to 225 pi over 180. And to simplify this out, I'm going to use a calculator. So this will become equal to 5 pi over 4. So this is the answer to part A, and now let's move on to part B. So it says to express 5 pi over 3 radians using degrees. And so it's a similar process to converting from degrees to radians, but instead of pi over 180 for our ratio over here, our fraction, we would want to flip it, so it would become times 180 over pi. Now these pi's cancel out, and we are left with 5 times 180 divided by 3. So this becomes 60. So our answer is 300 degrees. Now let's talk about the 6 basic trig functions. So, consider the unit circle centered at the origin and a point P with coordinates x, y on the unit circle. Let theta be an angle with an initial side that lies along the positive x-axis with a terminal side that is on the line segment OP. So with this information, we could define the values of the 6 trig functions for theta in terms of the coordinates x and y. So if we're looking at sine of theta, this is equal to y because sine is equal to opposite over adjacent. So that's basically y over 1, which is just y. Cosine theta is equal to adjacent over hypotenuse. This is y, it's x. And then tangent is equal to opposite over adjacent, which is y. This is equal to y over x. And cosecant is just the reciprocal of sine. Secant is just the reciprocal of cosine. And cotangent is just the reciprocal of tangent. And a little note over here, if x is equal to 0, then secant and tangent are undefined. And if y is equal to 0, then cosecant and cotangent are undefined as well. Now let's look at this. So it says for a point P is equal to x, y, which is a coordinate pair, on a circle of radius r and a corresponding angle theta, the coordinates x and y satisfy this. So cosine is equal to x over r, and this is also displayed in this picture over here. So suppose this is r. So according to this logic, then cosine over theta would be adjacent over hypotenuse, so x over r. So this works out. And then if you isolate x, this would mean that x is equal to r cosine theta. And the same thing goes with sine theta. So sine theta is opposite over adjacent, so that's why this is y over r. And if we were to isolate y, then we would get y is equal to r sine theta. So now let's look at this table. And this shows the values of sine and cosine at the major angles in the first quadrant. So when theta is equal to 0, then sine is equal to 0, and cosine is equal to 1. When theta is equal to pi over 6, then sine is equal to 1 over 2, and cosine is equal to the square root of 3 over 2. When it's pi over 4, then both sine and cosine are equal to root 2 over 2. And when theta is equal to pi over 3, then sine is equal to root 3 over 2, and cosine is equal to 1 over 2. And lastly, we have pi over 2 for this quadrant, and then in this case, sine is equal to 1, and cosine is equal to 0. And so there's a neat little trick to creating this table on your own, if you want it for tests or if you want it just in case. So what I would do is I would draw this would be sine theta, this would be cosine theta, and then on the top we could write the values. So this is 0, pi over 6, pi over 4, pi over 3, and pi over 2. Let's make columns. And so a way to kind of create the same table over here, but like in your head, is that you would want to count from 0 to 4 basically. So it would be 0, 1, 2, 3, 4. Okay, and then after that we divide everything by 4, and then we take the square root of everything. And I'm not doing this for 0, by the way, because 0 is just 0, so it just stays the same. But you could technically do all of this and it'll still end up being 0. So you take the square root of everything, and then this will turn into this will turn into 1 over 2. This would turn into the square root of 2 over 2. This would turn into the square root of 3 over 2. And this would turn into 1. And this is the exact same values listed down over here. And for cosine, it is the other way around. So we count from 4, 3, 2, 1, 0. Then we divide everything by 4. I'll do it for 0 this time, and then we take the square root of everything. So it's just the same values as sine, but it's just written in the opposite way. Let me finish this square root over here. And so if we were to simplify everything, this would become 0, 1 over 2, root 2 over 2, root 3 over 2, and then 1. And then this would go from 1 to root 3 over 2, root 2 over 2, 1 over 2, and then 0. So this is a way that you could replicate the same table, but in your mind. So now let's take a look at this example problem 1.23. It says to evaluate each of the following expressions. So A is sine of 2 pi over 3, and if we remember that this is pi over 3, and then you just want to swing it around to the other quadrant, and this whole thing right here, that is 2 pi over 3. So its reference angle will be pi over 3 like usual, so we could just use the value for pi over 3 over here. So that's why this answer is equal to root 3 over 2. But something I forgot to include is that depending on what trig function that you are working with, it is going to be either positive and negative in different quadrants. So this little table over here shows where things are positive and where things are negative. So everything is positive in the first quadrant. Sine and cosecant are positive in the second quadrant. Tangent and cotangent are positive in the third quadrant. And cosine and secant are positive in the fourth quadrant. And this little saying, all students take calculus, is there to help you remember what trig functions are positive in which specific quadrants. Yeah, so this is equal to 3 pi over 2, And because sine is positive in the second quadrant, we could keep it positive over here for our answer. Now let's take a look at B. So we have cosine of negative 5 pi over 6. So it starts over here, and then we go down something like that. This is pi over 6, and this is also in the third quadrant. So in this case, cosine would be negative. Okay, so this is negative 5 pi over 6, and so cosine of pi over 6, that is going to be root 3 over 2, but just to check, yes, it's root 3 over 2 over there. So, sorry about that. So this answer would be equal to negative root 3 over 2, because cosine is negative in the third quadrant. Now let's solve for part C. So the question is tan of 15 pi over 4. So the best way to go about this is to realize that you're able to split up this angle over here. So let's do just that. So 15 pi over 4 is the same thing as 8 pi over 4 plus 7 pi over 4. And 8 pi over 4 is the same exact thing as 2 pi. So now we're just looking at this angle right over here. So if we were to draw our sketch, then this would go all the way around like this. And our reference angle would be pi over 4. Okay, so I haven't taught you how to solve for tan functions, so I'll do it right now. So the best way to solve for tan functions is to go to whatever angle that you are working with. In this case, we're working with pi over 4 because that's our reference angle. And you want to divide the sine value for pi over 4 over the cosine value. So in this case, we are dividing root 2 over 2 divided by root 2 over 2. But that's just 1. So our answer is going to be 1. But because tan is in the last quadrant, and tan is only positive in the first quadrant and the third quadrant, this is going to be a negative 1. So these are the answers for this problem. So just to clarify about trig functions and how you would find the ratios behind them, let's go over this. So this is the key, and so O is equal to opposite, A is adjacent, and H is the hypotenuse. So sine is equal to opposite over a hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent, and then these are just reciprocals of these. So now let's look at example 1.24. It says a wooden ramp is to be built with one end on the ground and the other end at the top of a short staircase. If the top of the staircase is 4 feet from the ground and the angle between the ground and the ramp is 10 degrees, how long does the ramp need to be? Okay, so we've gained 2 pieces of information from this paragraph. So 1, the staircase is 4 feet from the ground, and 2, the angle between the ground and the ramp is 10 degrees. So with this, we can draw a diagram of what this situation looks like right now. So this is the ground. This is the 4 feet incline, and this is going to be the ramp. And so let's call this H, and this, we know theta is equal to 10 degrees. So what we're trying to solve for is we're trying to solve for H. And so what we learned earlier this right over here, we could use this sine. So sine theta is equal to y over r. So in this case, we could use this formula right over here. Y is equal to r sine theta. And then we could solve for the height, or sorry, the hypotenuse. So let's do that. So in this case, our y is the 4. So this is equal to y. So y is equal to h sine theta. H sine theta. And plugging in our values, we get 4 is equal to h times sine of 10 degrees. Now, to isolate h, we could just divide both sides by sine of 10 degrees, and we will get h is equal to 4 over sine of 10 degrees. And so I'm going to use my calculator. H is equal to 23.035. I'm assuming this is in feet, so this is the amount of wood we would need to build the ramp. Next up, we have some trig identities. So a trigonometric identity is an equation involving trigonometric functions that is true for all angles theta for which the functions are defined. So the first type of trig identities are reciprocal identities, and these are really easy. They are just the opposites of whatever it is. So sine theta is equal to 1 over cosecant theta, and I'm not going to go over this because it's pretty straightforward. But next up we have quotient identities. So tan theta is equal to sine divided by cosine. So sine theta divided by cosine theta. And this is why we were able to get this answer over here. Right over here, because we were able to divide sine divided by cosine, and that got us to tangent. And also the other way around, sorry, I went too far. And also the other way around, cotangent of theta is equal to cosine of theta over sine of theta. For Pythagorean identities, we have sine squared of theta plus cosine squared theta is equal to 1. Then we have 1 plus tan squared theta is equal to secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. And then we have addition and subtraction formulas. And so sine alpha plus or minus beta is equal to sine alpha times cosine beta plus or minus cosine alpha sine beta. And then when it's cosine instead of sine, cosine alpha plus or minus beta, then we get cosine alpha plus cosine beta. Then there's minus plus sine alpha sine beta. And so that means, because this minus is on the top, that means that when you're adding, then you're going to be subtracting over here. And when you're subtracting over here, you're going to be adding over here. Then we have double angle formulas, which is the last type of trig identity we're going to be going over. And so when it's sine 2 theta, this is the same thing as 2 sine theta times cosine theta. And cosine 2 theta has 3 different outputs. So the first one is 2 times cosine theta. The first one is 2 times cosine squared theta minus 1. The second one is 1 minus 2 times sine squared theta. And then the last one is cosine squared theta minus sine squared theta. Now let's look at example problem 1.25. It says, for each of the following equations, use a trigonometric identity to find all solutions. And so let's look at part A. I'll rewrite A down here. It says 1 plus cosine of 2 theta is equal to cosine theta. And so obviously we could tell that we have to do something about this cosine 2 theta. And using our trig identities, we should probably use this top value over here. So let's do that. Let's substitute that. So it'll become 1 plus 2 cosine squared theta minus 1 is equal to cosine theta. And so after that, these will cancel. And then if we subtract cosine theta from both sides, then we will get 2 cosine squared theta minus cosine theta is equal to 0. And then we could factor out a cosine, and this will become to be 2 cosine theta minus 1. This is all equal to 0. So now we could solve for the zeros basically, and so this will be cosine theta is equal to 0, and this would be 2 cosine theta minus 1 is equal to 0. And simplifying this one, then we see that, we could see that cosine of theta is equal to 1 over 2. So if cosine theta is equal to 0, then we know that theta must be pi over 2. And if cosine theta is equal to 1 over 2, then that means that theta must be pi over 3. So I forgot to mention that cosine also has another theta value. So when cosine of theta is equal to 1 over 2, theta is also equal to 7 pi over 3. Sorry, not 7 pi, 5 pi over 3. So this is another answer to this problem. Now let's work on part B. So let me write this over here. It is sine of 2 theta is equal to tan of theta. And so obviously we should realize that we have to do something about this sine 2 theta. So let's convert it to 2 sine theta times cosine theta is equal to, and this tan theta we can convert to sine theta over cosine theta. Now let's multiply both sides by cosine of theta, and we will get 2 sine theta times cosine squared theta is equal to sine of theta. Subtracting sine theta from both sides, we get 2 sine theta times cosine squared theta minus sine theta is equal to 0. And finally, we could factor out a sine to get 2 times cosine squared theta minus 1. And this is all equal to 0. So now we realize that sine theta is equal to 0, and 2 cosine squared theta is equal to 2 cosine squared theta minus 1 is equal to 0. So in this case, theta is equal to 0. And if we were to rearrange over here, this would become cosine is equal to, cosine theta is equal to 1 over root 2, and cosine of theta would be equal to root 2 over 2. So this means that theta is equal to pi over 4, and also 7 pi over 4. So these are the answers to part B. Now let's work on example problem 1.26. It says, prove the trigonometric identity 1 plus tan squared theta is equal to secant squared theta. And so first, let's use this trig identity. Sine squared theta plus cosine squared theta is equal to 1. This is one that we know that works. And then to convert this identity to this one, we could just divide both sides by cosine squared theta. And so what's going to happen is that this will become sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. which is just 1, is equal to 1 over cosine squared theta. And so this is equal to tan squared theta. This is plus 1. And then this is equal to secant squared theta. And this is the same thing as this function up over here. So that works. This is graphs and periods of trig functions. So let's first look at the sine function. So as you can see, the sine function is in this wavy fashion, just like the cosine function. But what's different about them is that they have different starting points. So sine of x, the function sine of x starts at the origin, and then it goes up, and then it starts the wavy pattern. But then cosine starts at 1, and then it goes down, and then it starts the wavy pattern. Cosecant of x and secant of x look pretty similar as well. They're just parabolas, upward and downward parabolas for both of them. And then tan of x and cotan of x also look the same, and they're in this wavy fashion as well. So consider this function over here. It says f of x is equal to a times cosine in parentheses b times in parentheses x minus alpha close parentheses all plus c. And so a is the vertical stretch, and that's by a factor of the absolute value of a. B is the component that changes the period, and the period over here is 2 pi over b. And then alpha is the horizontal shift, like left or right, and then c is the vertical shift, up or down. So this is a diagram that helps indicate this. And now let's work on the last problem for section 1.3, example problem 1.27. It says to sketch the graph of f of x is equal to 3 sine of 2 times x minus pi over 4 close parentheses all plus 1. So let's first list down the information that we have. So a is equal to 3, b is equal to 2, and so since the period is equal to 2 pi over b, the period would just be equal to pi. So this is important. Then we have a horizontal shift, pi over 4 units to the right. Then we have a vertical shift 1 unit up. Now let's attempt to draw an accurate graph of this function. So I'm just going to draw a really big graph like that. And then let's just go by increments of pi over 4. And because we know the period is pi, then I'm going to stop over here. And then we could go to the negatives. Okay, another thing we have to consider is the vertical shift 1 unit up. So I'm going to say that this is 1. So now our midline is over here. Let me do that better. Our midline is going to be over here. And on top of that, we have a horizontal shift 4 units to the right. So that means that our function is going to start over here. And I forgot to mention that b represents the horizontal compression. So that has to be taken into account when drawing this graph. And because a is equal to 3, it has to go up 3 units. 2, 3, and 4. So 4. And then down to, so this is -1, this is -2. So it has to go up to 4 and down to -2. So let's do this. I'll go up like this. Then I'll go down like that. Then after that, I'll come back up like this. And this is gonna be 5 pi over 4. So this is the full cycle of this graph. And then we can also go back to the negative side. So it's going to go something like this. And then go around like that. Then go 4. Something like that. And then bring it to negative 5 pi over 4 over here. So this is somewhat like that. It's going to be down, so I'm going to that. So it should look something like this. This is a rough graph though. So this is going to be it for 1.3 trigonometric functions, and I'll see you in 1.4, which is inverse functions.